Calorimetry practice problem number 1. A piece of metal with a mass of 4.68 grams absorbs 256 joules of heat when its temperature increases from 4 Celsius to 186 Celsius. What is the specific heat of this metal? And use the table below to identify the metal. So I'm asking you to actually calculate the specific heat of the metal. Okay? Since you have just single object to deal with, and you know that the energy is not being transferred from different things, I mean, it is being transferred, but I'm not giving you any other medium to deal with. This is what we call them a single system. Okay? So I'm going to go ahead and first write down the heat equation. Amount of heat energy can be calculated by the MCAT, and I am trying to calculate the specific heat capacity. Specific capacity, which is C. I'm going to go and rearrange, and also the temperature difference, again, is the final temperature minus initial temperature. Okay, ending temperature minus beginning temperature. Let me go ahead and rearrange my equation to calculate the C. C is equivalent to Q over M delta T. Now I'm going to go ahead and plug in my numbers. Energy was given to us, 256 joules. That goes into numerator, over mass of the metal, which is 4.68 grams, and multiplied by the delta T, the temperature difference. The final temperature, okay, the delta T is same thing as a TF minus TI. The final temperature, 186 minus 4 Celsius initial temperature. You go ahead and calculate this number, reporting 3 significant figures. You are going to be getting this value as the answer. And here's actually one thing you need to keep in mind, okay? Specific capacity will have a unit of joule per gram per Celsius, or sometimes Kelvin. But whether it's Kelvin or Celsius, it doesn't matter. They're gonna still give us the same result, because we are interested in absolute, not absolute, just the difference in the temperature. So it doesn't matter whether it's Kelvin or Celsius. Okay, so based on this, you know that the specific capacity was 0.301. So looking at this chart, you know that the answer is going to be strontium. Practice number 2. 150 gram of water, initially at 20.0 Celsius, are mixed with an unknown mass of iron, which was initially at 350.0 Celsius, when thermal equilibrium is reached, meaning two systems join together. The system has a temperature of 34.0 Celsius. So when you put water at 20 Celsius and iron with a 350.0 Celsius together, right, they're going to be exchanging the heat energy, and at the final exchange, we measure the temperature with 34.0. Okay, based on this, we have to calculate the mass of the iron. Specific capacity of iron is given, and also specific capacity of water is given. Okay, now this is a problem where you have two different systems that's exchanging the heat energy. Okay, you have water and you have the iron. Okay, you have two systems, water and iron, and water's initial temperature is 20.0 Celsius, while the iron's initial temperature is 350.0 Celsius. In other words, if water and iron are mixed together, heat will transfer from iron to water because iron is hotter than the water. So I'm gonna put the water as the receiving or gaining the heat energy, and then the iron is the one that's losing the energy. Again, the minus sign can be placed on either side; it doesn't matter. But remember, one side has to have a negative sign to start with. Okay, we know that the Q is equivalent to the MCAT, so I'm going to go ahead and rewrite the formula in terms of MCAT. Okay, so first one, the Q, MCAT over here, I'm going to write them in terms of water. So the mass of the water, specific capacity of water, and the delta T for the water, which is the final temperature of water minus initial temperature of water. That's equivalent to the MCAT version for the iron. Okay, remember, we have to include the minus for one side, and I'm going to just randomly put that onto the iron side. mass of the iron, specific capacity of the iron, and the TF, the final temperature of the iron, minus initial temperature of the iron, which will give us a delta T. Now, I am trying to calculate the mass of the iron. So I'm going to have to basically rewrite the whole formula in terms of mass of the iron. Okay, using the literal equation, you find out that this is going to be the equation for mass of the iron. Once you isolate the mass of iron, then it's easy. You just plug in the numbers. Mass of the water, 150 point gram, and then specific heat of water was a 4.18. Final temperature minus initial temperature, and then you have I'll write that one more time in terms of the iron down here, and then again putting all this in the calculator, obeying to the significant figures, you should be getting 61.9 grams. Now, practice problem 3 is really hard. Okay, my expectation is that you have to know how to do this. However, due to the time consumption of doing the problem like this one, okay, I'm not going to put a problem like this one onto your chapter exam. Okay, calculating the final temperature in this two system problem, the calorimetry problem, is really long process. Okay, and I repeat, you have to still know how to do this, okay, for your own good. And also, if you plan to take chemistry in college, absolutely you need to know this. However, for the time restraint, I'm not going to put the calculating final temperature into your chapter exam, okay? All right, so 97.0 gram sampleable gold is at 785 Celsius. It is heated up, it's really hot. And it's going to be dropped into 323 grams of water, which has an initial temperature of 15 Celsius. If gold has specific heat capacity given, and then what would be the final temperature of the mixture, okay? All right, so two systems, gold and water. Water is initial temperature 15 Celsius, gold is initial temperature 785. So water, okay, I'm sorry, this typo. When water and gold are mixed together, heat will transfer from gold to the water. All right, so the amount of heat energy that's gained by the water is equivalent to amount of heat energy that's given by the gold. Just that one side has to have a negative sign. All right, amount of energy is MCAT, so I'm going to go ahead and do the same thing from as the last problem. Just rewrite the two system in terms of MCAT. But keep in mind, final temperature of water and gold are actually the same, right? Because when they reach out to the heat equilibrium, the temperature of the both gold and water are going to be the same. So I'm going to go ahead and rewrite the TF of water is equivalent to TF of the gold. So I'm going to simplify that into just TF, basically just final temperature, regardless of the system. I'm trying to calculate the final temperature, so I'm going to have to actually get the final temperature. There are two places for this same variable. I'm going to have to first take this one out of the bracket. So I'm going to have to first get the bracket out of it. So I'm going to go ahead and distribute, right, these factors out there. So I'm going to go ahead and multiply mass of water and specific heat of water to the both terms. So when you do that, okay, I'm going to have to continue on the second page here. When I distribute these terms, what I get is this, right? Mass of water and M water, C water, multiplied to the TF. That's because I'm distributing this. Oops. I'm distributing this one into TF and also TI, and distributing this one to the TF and TI because that's the only way to get rid of the bracket, right? So once you do that, you get this. And then I'm going to have to solve for the TF. So I'm going to go ahead and move the terms containing TF to the one side, and then the terms that's not containing TF to the other side. So I'm going to go ahead and put this term and this term to the left, while the one that doesn't have a TF, like this term and this term, to the right. So let me go ahead and move the terms around, okay? Once I move it around, it's gonna look like this. Now I'm able to factor these first two terms in terms of TF, because I need to isolate the TF, so I'm gonna go ahead and factor it out. I'm gonna factor TF out to the front, and now put them into parentheses. Now, finally, if I divide both sides by this factored term and then divide by it, now I get this. So remember, I'm basically dividing the right side by this parenthesis term, right? So that this will cancel, and now this term is going to be placed on the denominator here, and then we get this fraction. Now we can go ahead and plug in the value for each one of them, and here it is. And then you have to consider the significant figure rules. You have a multiplication and also addition in the same equation. So I'm gonna go ahead and first multiply each term, okay? Obeying the significant figure rules. There are 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. And then when you're adding them together, okay, that's gonna be using the addition rule. So least accurate measurement, which is the nearest 100ths and nearest tens, and I get this. Now finally dividing it together, which is again obeying the division rule for the significant figure. 3 significant figures, 3 significant figures, you get the final number in 3 significant figures.